So here we go on to the next section of Chapter 8. Well, we skipped a section or two. But as you can see here, the title of this is Improper Integrals, which I always think is kind of funny. It's not like an integral that sits too close to you on the bus. It's more like an integral that has some sort of problem. And I'll begin by just kind of showing you a couple examples. Well, not examples, but a couple pictures. All right, so this is the topic of the day is improper integrals. Okay. Now, you know, we've done stuff like this for a long time now. You know, at least a semester and a half, where say I have some, you know, parabola that maybe looks like this. There's y, x, and let's call this one how about negative, so it's upside down, x minus 1 squared plus 1 to get it up a little bit. And then we could say that this is the 0, and then if we figured it out, that would be 2. And if I wanted to find the integral from 0 to 2 of negative x minus 1 squared dx plus 1, 0 to 2 of 1 dx, you know, that would be, we could figure that out, right? And that would give us some finite answer. And that makes sense, right? Well, we're bounded all the way around. Here's the shape. You know, it's got kind of this parabola on top, a straight line on the bottom, and there's some fixed amount of area in here that is determined by this definite integral here. All right? Yeah, we've been doing that for a long time. What's so special about that? Well, the point is to compare and contrast that. What if I did something like this, and I made this the y-axis and this the x-axis, and say I drew some function like and this is y equals e to the negative x. Okay, what does this look like? Well, when x equals 0, this equals 1, right? So right there. And as x gets really big, y gets really small, but it never gets all the way to 0. So what if we said, what is the integral from 0 to, well, since it never really ends, we've got to go all the way to infinity of e to the negative x dx. Okay. Now, is this finite? Is this finite? Right? Well, the easy response is no, because it just keeps going on forever, right? And so we can, I mean, if I said, how much paint do I need? And you started painting, it was, well, it never ends. So it can't be finite. So this is our first example of an improper integral. And Chapter 8 so far has been kind of clever tricks to solve some integrals that we come across. This is the first really topic in this class that involves a somewhat new concept. So we're going to, rather than deal with this infinity here, I'm going to rewrite this integral as the integral from 0 to, I'm going to say b, right? Some upper bound, and of e to the negative x dx, right? Well, to solve this integral, I could just say that, you know, u equals negative x, so du equals negative 1 dx, which means I need a negative sign, because I don't have a negative sign here, so I'll just put a negative sign in there, which means I have to put a negative sign out there. And this becomes the integral from, well, I can't use my limits here because my variable has changed. From e to the u du, which just equals e to the u and then I substitute my negative x back in there, so this becomes negative, negative, negative e to the negative x from 0 to b. All right, so this is all fine and good, but let's plug in some values here. So this is going to be negative, and that will be e to the negative b minus e to the 0, and so I don't like this negative negative here, so I'm going to change the order, and so that becomes e to the 0 minus e to the negative b. Alright, so let's think about this. I replaced this b, right, for my infinity. I stuck a b in for infinity, so what I really need to do is take the limit, oh yeah, here we go, limits again, as b approaches infinity of this thing, e to the 0 minus e to the negative b. Well, e to the 0 is 1, so really this is the limit as b approaches infinity of 1 minus, well, 1 over e to the b. Well, what happens here? As b gets really big, right, as it approaches infinity, this thing essentially goes away. So this whole thing equals 1. Right, that's it. No plus c or anything, because it's a definite integral. So even though I'm not putting really an upper bound on here, I'm extending this area all the way out here. The total area equals 1. It's a finite area, even though it's got an infinite limit of integration. So this is called an improper integral. Type 1. Like that. Okay. So let's take a look at a definition of that. I've got to pause for a second and go get that definition. Okay, so here we go. I just had to go find that that definition. So we've got this integral here, and the definition, formal definition is here. Now I like to read these and then say, does this make any sense, right? Because this math language is often very confusing. Integrals with infinite limits of integration are improper integrals of the type 1. If f of x is continuous on a to infinity, right? So from a to infinity, this function has to be continuous. Integral of f of x a to infinity, fx dx, is the limit as b approaches infinity. So all we did here is swap the b for the infinity sign of f of x. And then we can do the same thing from negative infinity, and we can do the same thing from negative infinity to infinity, which means we just have to swap out some integrals a couple times, right? In each case, if the limit is finite, we say the improper integral converges, and that the limit is the value of the improper integral. If the limit fails to exist, the improper integral diverges. So we have two key words here, converges and diverges. In this last example we did, we discovered that it does in fact converge, and it converges to the value of 1. So this one, I'm going to say converges. Okay, so good. Next up, let's take a look at another kind of what I think is a pretty cool one. We'll do, let's see, I'm not really sure I want to start these because this isn't really full-size paper. Let's say I've got the integral, but now I'm going to go, like I just did, all the way from negative infinity to infinity of 1 over 1 plus x squared dx. And if I were to sketch a plot of that, like that, and I go, it'll come up like that. At 0, right, it just becomes 1. And then it kind of goes back down like this. So I've got an idea of what this thing looks like. Now here we said we can go from negative infinity to infinity, and I've just got to pick some number in the middle, and obviously the number here in the middle would be 0, you know, because that would make sense. But I notice that the area on the left half of this is the same as the area on the right half of this. That's y and x here. So I'm only going to look at the right half to save myself a little bit of work. So in green, I'll just kind of highlight. I'm just going to just look at right half. And so instead of doing the integral from negative infinity to infinity, I am only going to look at the integral from 0 to infinity, right? So I just have one less limit to do of this same thing, 1 over 1 plus x squared dx. All right, well, how do we do this integral? Let's see, we could use substitution, u equals x squared, but then that would require an x up there, 1 plus x squared. Ooh, you know what? I bet if I went through all this and I used, say, tangent squared, or tangent, this would turn out to be the limit as b approaches infinity of inverse tangent of x from 0 to b. This is going to come up a lot. 1 over 1 plus x squared is always going to turn out to be this arctangent, the inverse tangent function. All right, but now we've got to figure out, well, when we stick a b in here, what happens? The inverse tangent of infinity, first of all. So this equals arctangent or inverse tangent of infinity minus arctangent, inverse tangent, whatever, of 0. Well, where does tangent go to infinity? Right, it's sine over cosine. So tangent, let's make a little side note here. Tangent equals sine over cosine. So this will go to infinity when cosine goes to 0. Well, where is cosine 0? It's pi over 2. So this is pi over 2 minus, where does the tangent go to 0? Well, where sine is 0, and that's at 0. So this thing really equals pi over 2. And but that was only half of it. So the green half here is, let's go down here. This green half is pi over 2. And so this half will also be pi over 2. So the total answer of this whole thing, from negative infinity to infinity, of 1 over x squared plus 1 dx equals, check this out, pi. Now I think that's really cool, that this, something that doesn't have anything to do with a circle, and doesn't have anything really to do with the trig functions or anything, that's just 1 over 1 plus x squared. This area, it's kind of like a hump, a hill. The area under there equals pi. So here's again this awesome number pi that comes up all the time, like Jean-Luc mentioned in that talk the other day. So this is another example of an improper integral that converges. Okay, so the fact that we talked about this improper integral type 1 might lead us to believe that there is another type, and that being the improper integral of type 2. So let's take a crack at another example here and see what we come up with. I'm going to look at the integral from, how about, negative 2 to 1 of 1 over x squared dx. All right, now we look at this integral like, that's a piece of cake, right? Because we can say this is more easily written as negative 2 to 1 of x to the negative 2 dx. And that is, so how does that work again? We raise the power by 1, so that goes up to x to the negative 1. But divide by the new power, old-fashioned integration from negative 2 to 1. So that will equal, well, how does that work? Negative 1 minus, because we put the 1 in here, and it's 1 over that to negative 1, so that's negative 1 minus, that becomes positive, so that's 1/2 equals 3/2, right? I think I did all that stuff correctly, except that I didn't. What if we look at more closely, what does the graph of this thing look like? I'm going to draw that down there, and then over here like this, x and y. 1 over x squared, what does that look like? It looks like this. It kind of goes up to infinity like that, and it comes back down like that. And if I took this area, so what happened here? It's not a nicely bounded area like that first one we did. There's some infinity stuff going on, some unbounded area in here that I just kind of blew right past, didn't I? I just went from -2 to 1, and I just kind of ignored the fact that I've got some infinite and some asymptotes, division by 0 issues in here. So we can't just simply do this. So I'm going to cross that out because we got a little careless, a little reckless there. So this raises or brings about a concept called this type 2, which you guys suspected was there. So an unbounded integral of the second type. If fx is continuous on a to b and discontinuous at a, okay, so that means if it was, notice the open parenthesis here, that so from a to b is no problem, but discontinuous at a, then we'd have to say, well, we'll take the limit as c approaches a from the right side. So for instance, if I was just going from 0 to 2 or 0 to 5, it's continuous all along here, but it's discontinuous right at that end border. I'd have to replace this left border with a limit. Likewise, if it was from the other way, so say from -5 to 0, I'd have to replace this 0 with a limit from the left this time, and that's what this little b to the left means. Finally, if fx is discontinuous at c, where c is somewhere between a and b and continuous on a to c and then c to b, this is the case that we actually have. We're going from -2 to 1, -2 to 1, but it's discontinuous somewhere in the middle, in this case 0. We've got to break it up. We've got to do it from the integral from a to c, which becomes, we've got a limit issue at c, and then from c to b, where we have to replace each of these with a limit. We'll do some examples like this, but I'm gonna pick a more interesting example to demonstrate this. So let's look at the integral from 0 to 2 of dx over root 4 minus x squared. All right, so right away you're looking at this and saying, oh, I know what kind of integral that's going to be. So how does this go? Well, can I just do this as integral, trig substitution, blah, 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 and do it? I don't know, because we have to look at these limits. Are there any problems? Will I run into any division by 0 issues on this with this 4 minus x squared? Sure. Well, where x equals 2. So if x equals 2, that's going to lead to div by 0. All right, so this is one of these cases where the right end is going to give me an issue. So I'm going to say this thing is going to be the limit as, pick your variable. In my notes I use t, I'm not sure why. As t approaches 2 from the left of the integral from 0 to t of dx over root 4 minus x squared. Okay. Now, back from chapter 8.3, 4 minus x squared, it's something minus x squared, so that leads us to think that we use the sine function as our substitution. And if we were to go through and do this whole thing, we discover that this would be the limit as t approaches 2 from the right of the arc sine function of, and it works out to be t over 2 or x over 2. And we're still going from 0 to t. And we plug this stuff in, equals the limit. And I'm just going to have you remember that it's, this approaching from the left here, of the arc sine of t over 2 minus the arc sine of 0 over 2, which is really just 0. And so that equals, where does the sine go to infinity? We have to think about that. Or no, as it approaches 2, right? So this is going to approach 2 from the lower side. So it's 1.9, 1.99, 1.999. So where does the sine equal 1? Well, that's at pi over 2. Minus, where does the sine equal 0? Well, that's at 0. So that equals pi over 2. So again, we're feeling pretty good because we had this kind of unbounded integral. Well, I should have drawn a picture of this first. We'll have asymptotes. We're at 2 and negative 2. Like this. Some nice asymptotes there. What's that painter's name, that Bob something or other? A happy little asymptote here and a happy little asymptote here. So that kind of goes, oop, I just erased. Stop that. Sometimes I've got this stylus kind of pen thing that I use on this tablet, and it's got all sorts of little buttons and clickers on it. So this thing is going to look roughly like this, and then back like this. And the area I'm really interested in, if I'm going from 0 to 2, is this area here. So we can see it's unbounded when we look up in the on the right edge of it. But nonetheless, again, it doesn't have anything to do with any trig functions, but it does because we get this pi over 2 out of it. It works out. So so far we can see that every time we've tried this, we've discovered that our integral does in fact turn out to be bounded. So at this point, we're feeling pretty good because we've got all these type 1 and type 2 integrals. The type 1 being we just go off to infinity in the limit, and type 2 being somewhere within the limits there's an infinite issue. And they always seem to converge upon one value. Okay. Well, let's take a look at another example where that may not be the case. So this is a classic example that I think is really important to cover. I'm going to say this one goes from 0 to 1. Let's pick something a little easier. How about just 1 over x dx? And we know we can rewrite that as a limit, right? Because where's the problem going to be? The problem is going to be right here, right? Because when we stick a 0 in here, bad news. So I'm going to rewrite this one as the limit as what? Let's say I'll use the variable t. As t approaches 0 from which side? From the right side. Alright, so the limit as t approaches 0 from the right. That's what that little plus means. And then I'm going to change that to the integral from t to 1 of 1 over x dx. Alright, so we're good there. And now this is a pretty easy integral to do, right? 1 over x is just natural log. So this becomes the limit as t approaches 0 from the right of the natural log of 1, natural log of 1 minus natural log of t. Okay, so we're feeling pretty good there. But the natural log of 1 is 0. That doesn't really depend on the t at all. 0 minus, well, the natural log of t, as t is really small, the natural log, let's kind of remember what the natural log looks like in case you don't. The natural log function looks something like this. And it goes off like this. So this is x, this is y, and this is y equals natural log of x. So as I approach 0 from the right, my natural log of what goes to negative infinity. Right, so this thing equals infinity. It does not converge on a certain value. So we can say that this one diverges. All right, so this one doesn't have a finite area. If I said, hey, paint this, let's say my original function, from 0 to 1 looks like this, and I'm looking to paint this area in here, right? If I said, hey, can you paint that? You'd have to say, no, I can't, because it takes an infinite amount of paint due to this part here. Okay, now in a separate video, I'm going to show a little different example that is conceptually a little tricky, but really shows a powerful technique and a powerful tool that we'll use later on this semester too. So that's it for this one. I hope that made some sense. We will talk again soon.